Welcome to the presentation of our project. I am Ayush and we will be running a Spark-based frequency pattern growth algorithm on a sample FP growth dataset. The presentation will start with a brief introduction to the components of Hadoop, the Spark architecture, and application flow. Next, we'll explain how the frequency pattern growth algorithm works along with parallel FP growth. Finally, a live demonstration of the algorithm will be shown on a two-node cluster. Hadoop is an open-source Java-based software platform that manages data processing and storage for big data applications. The platform works by distributing Hadoop big data and analytics jobs across nodes in the computing cluster, breaking them down into smaller workloads that can be run in parallel. Some key benefits of Hadoop are scalability, resilience, and flexibility. Hadoop consists of three main components: MapReduce, HDFS, and Yarn. MapReduce is a framework that allows code to be written and run at scale on a cluster. It processes big data by splitting it into smaller units. As a processing component, it's the heart of Hadoop. MapReduce algorithms have two components: map and reduce. Map takes input file and performs mapping tasks by processing and extracting important data into key value pairs. Recognizing is done before the output is sent to the reducer. Reducer works with multiple map functions and aggregates the pairs using their keys to produce the final output. HDFS, the file system that stores and manages big data files. It manages all the issues around large and distributed datasets, including resilience and partitioning. It splits files into blocks, creates block replicas, and stores them on different machines. It's built to access the streaming data seamlessly. Yarn's the default resource manager for big data applications, like Hive and Spark. It prepares the RAM and CPU to run data. Spark is an open source in-memory application framework for distributed data processing and iterative analysis on massive data volumes. Spark provides parallel and distributed processing, scalability, and fault tolerance on commodity hardware. It provides in-memory processing and creates a comprehensive, unified framework to manage big data processing. MapReduce creates iterations that require reads and writes on to disk on HDFS, which is time-consuming and expensive. Spark solves the read-write problems encountered with MapReduce by keeping much of the data required in memory and avoids expensive disk input-output, reducing overall time by order of magnitude. Spark follows a master-slave architecture with two main daemons: a cluster manager, manager daemon, and worker daemon, and cluster manager. Next, Chandan, I will take up.
Spark consists of the drive program and the executor program. Executor program works on the worker node and Spark starts additional executor process on a worker if there is enough memory and cores available. Similarly, executors can also take multiple cores of multi-threaded calculations. Spark distributes RDDs among the executor and communication occurs among the driver and the executors. The driver contains Spark jobs that the application needs to run and splits the job into tasks submitted to the executors. The driver receives the task result when executor completes the task. If Spark is an organization, the driver code would be the executive management of the company that makes decisions about allocation work, obtaining capital, and more. The junior companies are the executor who do the jobs assigned to them with the resources provided. The workers' nodes correspond to the physical office space that the employees occupy. You can add additional worker nodes to scale big data processing incrementally. Now, RDDs. Resilient distributed dataset are Spark's primary data abstraction. It is a collection of fault tolerant and immutable elements partitioned across the cluster's node, capable of receiving parallel operations. Spark uses a unique data structure called direct acyclic graph and an associated DAG scheduler to perform RDD operation. RDD transformations are considered lazy because Spark doesn't compute transformation results immediately. Instead, the results are computed when evaluated by actions. The vertices represent RDDs and the edges represent the transformation or actions. The DAG scheduler applies the graphical structure to run the tasks that use the RDD to perform transformation process. DAG helps enable fault tolerance. When a node goes down, Spark replicates the DAG and restores the node. Now, Vivan will continue the application.
The Spark application flow consists of many parallel and often related jobs, including multiple jobs resulting from multiple data sources, multiple data frames, and the actions applied to the data frame. Workflow can include jobs created by the Spark context in the driver program, jobs in progress running as the task in the executors, completed job transferring results back to driver or writing to the disk. Spark jobs divide into stages, which connected as a directed acyclic graph. A stage in a Spark job represents a set of tasks with narrow dependencies an executor can complete on the current data partition. Tasks from the current stage are scheduled on the cluster. As the stage completes all its tasks, the next dependent stage in the DAG begins. The job continues through the DAG until all stages complete. When application jobs are complete and the results are sent to the driver or written to the disk, the Spark context can be stopped either manually or automatically when the application exits. When the application UI server shutdowns, the UI no longer is available. To view the application UI after the application stops, event logging must be enabled. This means that all events in the application workflow are logged into a file and the UI can be viewed with the Spark history server. Now we move on to how the frequency pattern growth algorithm works. So let's talk about steps to be performed. Based on the transaction history of the items bought, we create some rules suggesting if a set of items is bought together, then it is likely that the output of the rule will also be bought along with them. These rules are generated by frequency pattern algorithm, which we will demonstrate with an example.
Transaction history where each ledger represents an item bought. The first step is to calculate the frequency of each item, and then we establish the minimum support. In this case, we took minimum support as 3. From here, we create a frequent pattern set where items included if and only if items frequency is greater than or equal to the minimum sample. Next, we create an ordered item set where we filter out all the items which are not included in the frequent pattern set. From here, we create a frequent pattern tree where we iterate over each of the ordered item set to create a tree. In the first iteration, FCA and we increment its count as we go down the path. Next iteration, FCABN. FCA represents the direct path to B, so we branch up BN, and the dotted line represents from old occurrence to new occurrence. Next, FB, CDP, and the final iteration creates a given frequent pattern tree from which we are going to create a conditional pattern basis. The conditional pattern bases are given an item, we need to find all the possible paths that the frequent pattern tree is taking to reach that item. So M, FCAN, and then we give the count as the frequency in the frequent pattern tree. So M equals 2, so FCA equals 2. Next, FCAB, which we just done, but M count over here is 1. Like that, we do it for each and every single item. You can see some of the items have been circled with a dotted circle in the past. That indicates that these items are common in all the parts. For example, for item FC and A occurs in both the parts. But as you can see, for item B, F only occurs in this part, but it does occur in the last part, so it is not circular. Now from these circular common items for each part, we can create a conditional frequent pattern tree. Conditional frequent pattern tree, given all common items with their current frequency, we are mapping out the conditional frequent pattern tree for M, F equals to B, C equals to 3, and A equals to 3 for M. As you can see, we had no common items, that was a random path. That's why the set is null. And from this pattern tree, we create our frequent patterns, where we are just mapping out all the possible combinations that are possible. For example, for M, F, C, and A, and the possible combinations are MF, MC, MA, MFC, MCA, MFA, and MCFA. Now from this, the last step is to obtain the rules by considering one frequent pattern and calculating its confidence. Now you can see that MF is a possible frequent pattern rule, but FM is also another possible rule. We need to consider both directions. After calculating the confidence for all possible rules, it's a satisfied minimum confidence that we can consider that as an association rule.
This is Ayushi, and we'll be talking about parallel FP growth. Input data of transactions is given to the cluster having P processors and P CPUs to run the map. Sharding takes place where the database is divided into P successive parts, called shards, and stored them on P different nodes. Parallel FP growth distributes the work of the growing suffix tree, and suffix analysis of those transactions is done. Each machine executes with an independent group of mining tasks, that is, groups are formed in the dataset, and each node performs mining operation independently. In the end, merging of all the results is done. Parallel counting is performed on each shard via support counters, and then merging of the values together in the reducing phase is done. This creates a frequent pattern set. It's more scalable than computing the results in a single machine. Now let's see what happens in parallel processing. A computer stores data and moves it from its storage capacity to a computer capacity and back to storage once important results are obtained. Big data can't be fit in a single computer and requires multiple computers to process that data in parallel. Linear processing breaks down a problem statement into a set of instructions and executes sequentially till all instructions are executed. It begins from the start if an error occurs and gets resolved. It's inefficient and time consuming for complex problems like big data. Parallel processing also breaks down the problem statement but distributes the instructions to different nodes to execute in parallel. Error resolving is local to that node only and won't disturb the other node execution. It reduces processing time, requires less memory and processing requirements, increased flexibility of adding or reducing nodes, which reduces infrastructure expenses. Technologies like Hadoop and Spark help to achieve parallel processing over a cluster and ensures consistency, scalability, and fault tolerance. Now let's go to the live demonstration. Sharan will be presenting.
Now we start the live session of our presentation. Here we have a master and a slave. In the master, we can see all the master related daemons running along with the history server. Now if we SSH into slave and we type in JPS, we can see all the slave related daemons running. This is the command to submit the jar file into our Spark cluster, and it will run the given class inside the jar file located at the given location. The application has ended and we can see the output. It first printed all the conditional bases and then it printed all the association rules for the given dataset. Now looking at our history server, This is the application we have currently run. It has completed all its tasks and took only 8 stages to complete, as shown here. And this is the environment on which software and hardware we ran the algorithm. And this concludes our live demo. These are our team members, and this concludes our presentation.